This presentation is delivered by the Stanford Center for Professional Development.
Okay, good morning. Welcome back. What I want to do today is actually wrap up our discussion on learning theory and going to start by talking about Bayesian statistics and regularization. And then take a very brief digression to tell you about online learning. And most of today's lecture will actually be on various pieces of advice for applying machine learning algorithms to problems like, like your project or other problems you may go work on after you graduate from this class. Let's start by talking about Bayesian statistics and regularization. So you remember from last week, we started to talk about learning theory and we learned about bias and variance. And I guess in the previous lecture, we spent most of the previous lecture talking about algorithms for model selection and for feature selection. We talked about cross-validation, right? So most of the methods we talked about in the previous lecture were ways for you to try to simplify the model. So for example, the feature selection algorithms we talked about gives you a way to eliminate a number of features so as to reduce the number of parameters you need to fit and thereby reduce overfitting. Right? You remember that? So feature selection algorithms choose a subset of the features so that you have less parameters and you might be less likely to overfit. Right? What I want to do today is talk about a different way to prevent overfitting and is a method called regularization, and is a way that lets you keep all the parameters. So here's the idea, and I'm going to illustrate this example with, say, linear regression. So if you take the linear regression model, the very first model we learned about, right? We said that we would choose the parameters via maximum likelihood, right? And that meant that, we would choose the parameters theta that maximize the probability of the data. We choose parameters theta that maximize the probability of the data we observe, right? And so, to give this sort of procedure a name, this is one example of what's called a frequentist procedure. And frequentists you can think of as sort of maybe one school of statistics. And the philosophical view behind writing this down was we envisioned that there was some true parameter theta out there that generated the x's and the y's. That there's some true parameter theta that govern housing prices of y as a function of x. And we don't know what the value of theta is. And we'd like to come up with some procedure for estimating the value of theta. Okay? And so maximum likelihood is just one possible procedure for estimating the unknown value for theta. And in the way we formulated this, theta was not a random variable. Right? That's why I said, so theta is just some true value out there. It's not random or anything. We just don't know what it is. And we have a procedure called maximum likelihood for estimating the value for theta. So this is one example of what's called a frequentist procedure. The alternative to the frequentist school of statistics is the Bayesian school, in which we're going to say that we don't know what theta is, and so we will put a prior on theta. Okay, so in the Bayesian school, we'll say, well, don't know what the value of theta is, so let's represent our uncertainty over theta with a prior. So for example, our prior on theta may be a Gaussian distribution with mean 0 and covariance matrix given by tau squared I. Okay, and so actually, if I use S to denote my training set, well, right. So theta represents my beliefs about what the parameters are, in the absence of any data. So not having seen any data, theta represents what I think theta, the prior represents what I think theta is most likely to be. And so given a training set S, in the Bayesian procedure, we would, calculate the probability, or the posterior probability of my parameters given my training set. And let's write this on the export. So my posterior on my parameters given my training set by Bayes' rule, this will be proportional to, this. Right, so by Bayes' rule. Just call it posterior. And this distribution now represents my beliefs about what theta is after I've seen the training set. And when I now want to make a new prediction on the price of a new house, right, on the new input x, I would say that, well, the distribution over the possible housing prices for this new house, I'm trying to estimate the price of, say, given the size of the house, the features of the house x, and the training set I had previously, is going to be given by an integral over my parameters theta of probability of y given x comma theta, and times the posterior distribution of theta given the training set. Okay? And in particular, if you want your prediction to be the expected value of y given the inputs x in the training set, you would say integrate over y times your posterior. Okay? You take an expectation of y with respect to your posterior distribution. Okay? And you notice that when I was writing this down, so with the Bayesian formulation, I now start to write p of y given x comma theta, because this formula now is the probability of y conditioned on the values of the random variables x and theta. So I'm no longer writing semicolon theta, I'm writing comma theta, because I'm now treating theta as a random variable. Right. So all this is somewhat abstract, but this is, and it turns out, actually, let's check, other questions about this? Let's try to make this slightly more concrete. It turns out that for many problems, both of these steps in the computation are difficult, because if theta is an n+1 dimensional vector, is an n+1 dimensional parameter vector, then this is an integral over an n+1 dimensional, over Rn+1. And just numerically, it's very difficult to compute integrals over very high dimensional spaces, right? So usually this integral, usually it's hard to compute the posterior on theta, and it's also hard to compute this integral if theta is very high dimensional. There are a few exceptions for which this can be done in closed form, but for many learning algorithms, say Bayesian logistic regression, this is hard to do. And so what's commonly done is to take the posterior distribution, and instead of actually computing a full posterior distribution, p of theta given s, we'll instead take this quantity on the right-hand side and just maximize this quantity on the right-hand side. So let me write this down. So commonly, instead of computing the full posterior distribution, we will choose the following. Okay, we'll choose the what's called the MAP estimate, on the maxima posteriori estimate of theta, which is the most likely value of theta, most probable value of theta under your posterior distribution. And that's just argmax P of theta. And then when you need to make a prediction, right, you would just predict, say, well, using your usual hypothesis and using this map value of theta in place of as the parameter vector that you choose. Okay. And notice the only difference between this and standard maximum likelihood estimation is that when you're choosing, instead of choosing the maximum likelihood value for theta, you're instead maximizing this, which is what you had for maximum likelihood estimation, and then times this other quantity, which is the prior. Right? Let's see. One intuition is that if your prior is theta being Gaussian with mean 0 and some covariance, then for a distribution like this, most of the probability mass is close to 0, right? So this is a Gaussian centered around the point 0, and so most of your probability mass is close to 0. And so the prior distribution, instead of saying that you think most of the parameters should be close to 0. And if you remember our discussion on feature selection, right? If you eliminate a feature from consideration, that's the same as setting a certain value of theta to be equal to 0. Right? So if you set theta 5 to be equal to 0, that's the same as eliminating feature 5 from your hypothesis. And so this is a prior that drives most of the parameter values to 0, to values close to 0. And you think of this as doing something analogous, doing something reminiscent of feature selection. Okay? It turns out that with this formulation, the parameters won't actually be exactly 0, but many of the values will be close to 0. And I guess in pictures, if you remember, I said that if you have, say, 5 data points and you fit a 4th order polynomial, well, I think that had too many bumps in it, but never mind. If you fit a very high polynomial to a very small data set, you can get these very large oscillations if you use maximum likelihood estimation, right? In contrast, if you apply this sort of Bayesian regularization, you can actually fit a high order polynomial, but still get sort of a smoother and smoother fit to the data as you decrease tau. So as you decrease tau, you're driving the parameters to be closer and closer to 0. And that, in practice, is sort of hard to see, but you can take my word for it. As tau becomes smaller and smaller, the curves you tend to fit to your data also become smoother and smoother. And so you tend less and less to overfit, even when you're fitting a large number of parameters. Okay. Let's see. And one last piece of intuition that I'll just toss out there. You get to play with this particular set of ideas more in problem set 3, which we'll post online later this week, I guess. Is that whereas maximum likelihood tries to minimize, say, this. Oops. Right? Whereas maximum likelihood for, say, linear regression turns out to be minimizing this. It turns out that if you add this prior term there, it turns out that the optimization objective you end up optimizing turns out to be that, where you add an extra term that penalizes your parameter theta as being large. And so this ends up being an algorithm that's very similar to maximum likelihood, except that you tend to keep the parameters small. And this has the effect. Again, it's kind of hard to see, just take my word for it, that shrinking the parameters has the effect of keeping the functions you fit to be smoother and less likely to overfit. Okay. Okay. Hopefully this will make more sense when you play with these ideas a bit more in the next problem set. Let me just check questions about all this.
So the smoothing behavior is in the case of Gaussian, right? If you put some other prior, you may actually get a different sort of effect.
Let's see. Yeah, so it depends on, well, most priors with most of the mass close to 0 will get this effect, I guess. And just by convention, the Gaussian prior is what's used the most common for models like logistic regression and linear regression of generalized linear models. There are a few other priors that are sometimes used, like a Laplace prior, but all of them will tend to have these sorts of smoothing effects. Cool. And so it turns out that for problems like text classification is problems with like 30,000 features or 50,000 features, where it seems like an algorithm like logistic regression would be very much prone to overfitting. Right? So imagine trying to build a spam classifier. Maybe you have 100 training examples, but you have 30,000 features, 50,000 features. That seems to clearly be prone to overfitting, right? But it turns out that with this sort of Bayesian regularization, with actually exactly Gaussian, logistic regression becomes a very effective text classification algorithm with this sort of Bayesian regularization. Alex?
So to pick lambda, do you generally use cross-validation?
Yeah, right. And to pick either tau squared or lambda. I think the relation is lambda equals 1 over tau squared. But right, to pick either tau squared or lambda, you could use cross-validation, say. Right. Okay, cool. So, all right. That was all I wanted to say about methods for preventing overfitting. What I want to do next is just spend 5 minutes talking about online learning, and this is sort of a digression. I say when you're designing the syllabus of a class, I guess sometimes there are just some ideas you want to talk about but can't find a very good place to fit in anywhere. So this is one of those ideas that must seem a bit disjointed for the rest of the class, but just want to tell you a little bit about it. Okay. So here's the idea. So far, all the learning algorithms we talked about are what's called batch learning algorithms, where you're given a training set, and then you get to run your learning algorithm on the training set, and then maybe you test on some other test set. And there's another learning setting called online learning, in which you have to make predictions even while you're in the process of learning. So here's how the problem proceeds. Right. I'm first going to give you x1. Let's say there's a classification problem. So I'm first going to give you x1, and then I'm going to ask you, can you make a prediction on x1? Is the label 1 or 0? You've not seen any data yet. And so you make a guess, right? You call your guess y hat 1. And after you made your prediction, I will then reveal to you the true label y1. Okay? And not having seen any data before, your odds of getting the first one right are only 50%, right? If you guess randomly. And then I'll show you x2. And then I'll ask you, can you make a prediction on x2? And so you now maybe able to make a slightly more educated guess and call that y hat 2. And after you've made your guess, I'll reveal the true label to you, and so on. Okay? Then I'll show you x3, and then you make your guess, and learning proceeds as follows. So this is a different model of machine learning than batch learning, and it models settings where you have to keep learning even as you're making predictions. Okay, so I don't know. Imagine setting a website and you have users coming in, and as the first user comes in, you need to start making predictions already about what the user likes or dislikes. And there's only, as you're making predictions, you get to show more and more training examples. So in online learning, what we care about is the total online error. Which is sum from I equals 1 to m, say, if you get a sequence of m examples altogether. Indicator y has I not equal to yi. Okay, so the online error is the total number of mistakes you make on a sequence of examples like this. It turns out that many of the learning algorithms you have, well, actually pretty much all the learning algorithms you've learned about can be applied to this setting. One thing you could do is, well, when you're asked to make a prediction on y hat 3, right? One simple thing you could do is, well, you've seen some number of training examples up to this point, so you can just take your learning algorithm and run it on the examples, leading up to y hat 3. So just run the learning algorithm on all the examples you've seen previous to being asked to make a prediction on a certain example, and then use your learning algorithm to make a prediction on the next example. It turns out that there are also algorithms, especially the algorithms that we saw that could use stochastic gradient descent, that can be adapted very nicely to this. So as a concrete example, if you remember the perceptron algorithm, say, right, you would say initialize the parameter theta to be equal to 0. And then after seeing the ith training example, you'd update the parameters using you've seen this rule all the times now, right? Using the standard perceptron learning rule. And the same thing for if you were using logistic regression, you can then again, after seeing each training example, just run, essentially run one step of stochastic gradient descent or stochastic gradient descent on just the example you saw. Okay, and so the reason I fit this into the sort of quote learning theory section of this class was because it turns out that sometimes you can prove fairly amazing results on your total online error using algorithms like these. I won't actually show, I don't actually want to spend the time in the main lecture to prove this, but for example, you can prove that when you use the perceptron algorithm, then even when the features xi may be infinite dimensional feature vectors, like we sort of saw, right, for support vector machines, and sometimes infinite feature dimensional vectors when you use kernel representations. Okay, so it turns out you can prove that when you use the perceptron algorithm, even when the data is maybe extremely high dimensional, it seems like you'd be prone to overfitting, right? You can prove that so long as the positive and the negative examples are separated by a margin, right? So long as in this infinite dimensional space, so long as there is some margin gamma separating the positive and negative examples, you can prove that the perceptron algorithm will converge to a hypothesis that perfectly separates the positive and negative examples. Okay, and so after seeing only a finite number of examples, it will converge to a decision boundary that perfectly separates the positive and negative examples, even though you may be in an infinite dimensional space. Okay, so let's see. The proof itself would take me sort of almost an entire lecture to do, and there are sort of other things that I want to do more than that. So you want to see the proof of this yourself is actually written up in the lecture notes that I post online. For the purposes of this class's syllabus, the proof of this result, you can treat this as optional reading. And by that I mean, it won't appear on the midterm, and you won't be asked about this specifically on the problem sets. But I thought it'd be, I know some of you are curious after the previous lecture for why you can prove that SVMs can have bounded VC dimension even in these infinite dimensional spaces, and how do you prove things in these, how do you prove learning theory results in these infinite dimensional feature spaces? And so the perceptron bound that I just talked about was sort of the simplest instance I know of that you can sort of read in like half an hour and understand it. So if you're interested, there are lecture notes online for how this perceptron bound was actually proved. It's a very pretty result. You can prove it in like a page or so. So go ahead and take a look at that if you're interested. Okay, but regardless of the theoretical results, the online learning setting is something that comes up reasonably often, and so just these algorithms based on stochastic gradient descent often work very well for them. Okay, any questions about this before I move on? All right, cool. So the last thing I want to do today, and was the majority of today's lecture, actually, can I switch to PowerPoint slides, please? Is I actually want to spend most of today's lecture talking about advice for applying different machine learning algorithms. And so, you know, right now, all of you have I think, a good understanding of really the most powerful tools known to humankind in machine learning, right? And what I want to do today is give you some advice on how to apply them really powerfully, because, you know, the same tool, it turns out that you can take the same machine learning tool, say logistic regression, and you can ask two different people to apply it to the same problem, and sometimes one person will do an amazing job and work amazingly well, and the second person will sort of not really get it to work, even though it's exactly the same algorithm, right? And so what I want to do today, and the rest of the time I have today, is try to convey to you, you know, some of the methods for how to make sure you really know how to get these learning algorithms to work well in problems. So just some caveats on what I'm going to, I guess, talk about in the rest of today's lecture. Some of what I'm going to talk about is actually not very mathematical, but there's also some of the hardest, conceptually most difficult material in this class to understand. All right? So this is not mathematical, but this is not easy. And I'll say, caveat, some of what I'll say today is debatable. I think most of the good machine learning people will agree with most of what I say, but maybe not everything I say. And some of what I'll say is also not good advice for doing machine learning research. I'll say more about this later. What I'm focusing on today is advice for how to just get stuff to work. If you're working in a company and you want to deliver a product, if you're building a system and you just want your machine learning system to work. Okay? Some of what I'm about to say today isn't great advice if you go to invent a new machine learning algorithm, but this is advice for how to make a machine learning algorithm work and deploy a working system. So three key ideas I want to talk about are: one, diagnostics of debugging learning algorithms. Second, I want to talk briefly about error analyses and ablative analysis. And third, I want to talk about just advice for how to get started on a machine learning problem. And one theme that will come up later is, turns out you've heard about premature optimization, right, in writing software. This is when someone over-designs from the start. When someone is writing a piece of code and they choose a subroutine to optimize heavily, and maybe write a subroutine in assembly or something. And that's often, and many of us have been guilty of premature optimization, where we're trying to get a piece of code to run faster, and we choose part of the piece of code and re-implement it in assembly and really tune it and get it to run really quickly. And it turned out that wasn't the bottleneck in the code at all, right? And we call that premature optimization. And in like our undergraduate programming classes, we warn people all the time not to do premature optimization, and people still do it all the time, right? And turns out a very similar thing happens in building machine learning systems, that many people are often guilty of what I call premature statistical optimization, where they heavily optimize part of a machine learning system, and that turns out not to be the important piece. Okay? So I'll talk about that later as well. So let's first talk about debugging learning algorithms. Excuse me. As a motivating example, let's say you want to build an anti-spam system. And let's say you've carefully chosen a small set of 100 words to use as features. Right? So instead of using 50,000 words, you've chosen a small set of 100 features to use for your anti-spam system. And let's say you implement Bayesian logistic regression, implement gradient descent, and you get 20% test error, which is unacceptably high. Right? So this is Bayesian logistic regression. It's just like maximum likelihood, but with that additional lambda squared term, and we're maximizing rather than minimizing, which is why. So there's a minus lambda theta squared instead of plus lambda theta squared. So the question is, you implemented your Bayesian logistic regression algorithm, and you test on your test set, and you got unacceptably high error. So what do you do next, right? So one thing you could do is think about the ways you could improve this algorithm. And this is probably what most people will do. So, well, let's sit down and think what could have gone wrong. And then when you try to improve the algorithm, Well, obviously, having more training data can only help. So what you do is try to get more training examples. Maybe you suspect that even 100 features was too many, so you might try to get a smaller set of features. What's more common is you might suspect your features aren't good enough, so you might spend some time, look at the email headers, see if you can figure out better features for finding spam emails or whatever. Right, right. So just sit around and come up with better features, such as for email headers. You might also suspect that gradient descent hasn't quite converged yet, and so let's try running gradient descent a bit longer to see if that works. And clearly that can't hurt, right? Let's just run gradient descent for longer. Or maybe you remember hearing from the class that maybe Newton's method converges better. So let's try that instead. We want to tune the value for lambda. Not sure if that was the right thing. Or maybe you even want to try an SVM, because maybe you think an SVM might work better than logistic regression. So I only listed 8 things here, but you can imagine if you're actually sitting down building a machine learning system, the options to you are endless. You can think of hundreds of ways to improve a learning system. And some of these things, like, well, getting more training examples, surely that's going to help. So that seems like it's a good use of your time, right? And it turns out that this approach of picking ways to improve the learning algorithm and picking one and going for it, it might work in the sense that it may eventually get you to a working system, but often it's very time consuming, and I think is often a largely a matter of luck, whether you end up fixing what the problem is. In particular, these 8 improvements all fix very different problems, and some of them will be fixing problems that you don't have. And if you can rule out 6 of 8 of these, say, you could, if by somehow looking at the problem more deeply, you can figure out which one of these 8 things is actually the right thing to do, you can save yourself a lot of time. So let's see how we go about doing that. The people in industry and in research that I see that are really good will not go and try to change the learning algorithm randomly. There are lots of things that will, quote, obviously improve your learning algorithm. But the problem is there's so many of them, it's hard to know what to do. So the people I know that are really good will instead run various diagnostics to figure out what the problem is, and then fix what the problem is. Okay. So for our motivating story, right, we said, let's say Bayesian logistic regression's test error was 20%, which let's say is unacceptably high. And let's suppose you suspect that the problem is either overfitting, so it's high bias, or you suspect that maybe you have too few features to classify spam. So it's, oh, excuse me, I think I wrote that wrong. Let's suppose let's forget the text. Suppose you suspect the problem is either high bias or high variance. And some of the text here doesn't make sense. And you want to know if you're overfitting, which would be high variance, or if you have too few features to classify spam, which is high bias. I have those 2 reversed, sorry. Okay. So how can you figure out whether the problem is one of high bias or high variance? Right? So it turns out there's a simple diagnostic you can look at. They'll tell you whether the problem is high bias or high variance. If you remember the cartoon we'd seen previously for high variance problems, when you have high variance, the training error will be much lower than the test error. Right? When you have a high variance problem, that's when you're fitting your training set very well. That's when you're fitting a 10-folded polynomial to 11 data points. Right? And that's when you're just fitting the data set very well. And so your training error will be much lower than test error. And in contrast, if you have high bias, that's when your training error will also be high. Right? That's when your data is quadratic, say, but you're fitting a linear function to it, and so you aren't even fitting your training set well. So just in cartoons, I guess, this is what a typical learning curve for high variance looks like. On the horizontal axis, I'm plotting the training set size, m, right? And on the vertical axis, I'm plotting the error. And so, let's see, as you increase, if you have a high variance problem, you notice that as the training set size m increases, your test set error will keep on decreasing. And so this sort of suggests that, well, if you can increase the training set size even further, maybe if you extrapolate the green curve out, maybe the test set error will decrease even further. Right? Another thing that's useful to plot here is, let's say the red horizontal line is the desired performance you're trying to reach, Another useful thing to plot is actually the training error, right? And it turns out that your training error will actually grow as a function of the training set size. Because the larger your training set, the harder it is to fit, your training set perfectly, right? So this is just a cartoon, don't take it too seriously, but in general, your training error will actually grow as a function of your training set size. Because small training sets, if you have one data point, it's really easy to fit that perfectly, but if you have 10,000 data points, it's much harder to fit that perfectly, right? And so another diagnostic for high variance, and the one that I tend to use more, is to just look at training versus test error. And if there's a large gap between them, then this suggests that getting more training data may allow you to help close that gap. Okay? So this is what the cartoon will look like when, in the case of high variance. This is what the cartoon looks like for high bias, right? If you look at the learning curve, you see that the curve for test error has flattened out already, and so this is a sign that if you get more training examples, if you extrapolate this curve further to the right, it's maybe not likely to go down much further. And this is a property of high bias, that getting more training data won't necessarily help. But again, to me, the more useful diagnostic is if you plot training error as well. If you look at your training error as well as your holdout test set error, if you find that even your training error is high, then that's a sign that getting more training data is not going to help. Right? In fact, if you think about it, training error grows as a function of your training set size. And so if your training error is already above your level of desired performance, then getting even more training data is not going to reduce your training error down to the desired level of performance, right? Because your training error sort of only gets worse as you get more and more training examples. So if you extrapolate further to the right, it's not like this blue line will come back down to the level of desired performance, right? It's just stay up there, okay? So for me personally, I actually, when I look at the curve, like the green curve on test error, I actually personally tend to find it very difficult to tell if the curve is still going down or if it's asymptote. Sometimes you can tell, but very often it's somewhat ambiguous. So for me personally, the diagnostic I tend to use the most often to tell if I have a bias problem or a variance problem is to look at training and test error and to see if they're very close together or if they're relatively far apart. Okay? And so, going back to the list of fixes, look at the first fix. Getting more training examples is a way to fix high variance, right? If you have high variance problem, getting more training examples will help. Trying a smaller set of features that also fixes high variance, right? Trying a larger set of features or adding email features, these are solutions that fix high bias. Right? So if high bias being if your hypothesis was too simple, if you didn't have enough features. Okay? And so quite often you see people working on machine learning problems and they'll remember that getting more training examples helps. And so they'll build a learning system, build an anti-spam system, and it doesn't work. And then they'll go off and spend lots of time and money and effort collecting more training data because they'll say, oh, well, getting more training data is obviously got to help. But if they had a high bias problem in the first place and not a high variance problem, it's entirely possible to spend 3 months or 6 months collecting more and more training data, not realizing that it couldn't possibly help. And so this actually happens a lot, even to, in Silicon Valley and companies. This happens a lot. There'll often be people building various machine learning systems, and you often see people spending 6 months working on fixing a learning algorithm, and you could have told them 6 months ago that that couldn't possibly have helped, but because they didn't know what the problem was they easily spend 6 months trying to invent new features or something, and you see this surprisingly often. It's somewhat depressing. You could have gone to them and told them, I could have told you 6 months ago that this is just not going to help. The 6 months is not a joke. You actually see this. And in contrast, if you actually figure out the problem is one of high bias or high variance, then you can rule out two of these solutions and save yourself many months of fruitless effort. Okay. I just want to talk about these four at the bottom as well, but before I move on, let me just check if the questions about what I've talked about so far. Okay, cool. So bias versus variance is one thing that comes up often. This bias versus variance is one common diagnostic. And so for other machine learning problems, it's often up to your own ingenuity to figure out your own diagnostics to figure out what's wrong. Right? So if a machine learning algorithm isn't working, very often it's up to you to figure out, to construct your own tests. Like, do you look at the difference between training and test error, or do you look at something else? It's often up to your own ingenuity to construct your own diagnostics to figure out what's going on. What I want to do is go for another example. Right? And this one's slightly more contrived, but I'll illustrate another common question that comes up, and another one of the most common issues that comes up in applied learning algorithms. So in this example, it's slightly more contrived. Let's say you implement Bayesian logistic regression, and you get 2% error on spam mail and 2% error on non-spam mail. Right? So it's rejecting, 2% of is rejecting 98% of your spam mail, which is fine. So 2% of all spam gets through, which is fine. But is also rejecting 2% of your good email, right? 2% of the email from your friends, and that's unacceptably high, let's say. And let's say that a support vector machine using a linear kernel gets 10% error on spam and 0.01% error on non-spam, which is more of the acceptable performance you want. And let's say for the sake of this example, let's say you're trying to build an anti-spam system, right? Let's say that you really want to deploy logistic regression to your customers because of computational efficiency, or because you need to retrain overnight every day, and because logistic regression just runs more easily and more quickly or something. Okay? So let's say you want to deploy logistic regression, but it's just not working that well. So question is, what do you do next? So turns out that the issue that comes up here, one other common question that comes up is the question of, is the algorithm converging? So you might suspect that maybe the problem with logistic regression is just not converging. Maybe you need to run it from iterations. It turns out that, again, if you look at the optimization objective, say logistic regression is, let's say, optimizing J of theta. It actually turns out that if you look at the optimization objective as a function of the number of iterations, excuse me, if you look at this curve, it sort of looks like it's going up, but it sort of looks like it's asymptote. And when you look at these curves, it's often very hard to tell if the curve has already flattened out. Right? You look at these curves a lot. So you can ask, well, has the algorithm converged? If you look at the J of theta like this, it's often very hard to tell. You could run this 10 times as long and see if it's flattened out. And you run this 10 times as long, and it'll often still look like maybe it's going up very slowly or something. Right? So can we come up with a better diagnostic for whether logistic regression has converged than looking at this curve? The other question you might wonder, the other thing you might suspect is a problem is, are you optimizing the right function? So what you care about, right, in spam, say, is a weighted accuracy function like that. So A of theta is, sum over your examples of some weight times whether you got it right. And so the weight may be higher for non-spam than for spam mail, because you care about getting your predictions correct for spam email much more than non-spam mail, say. So let's say A of theta is the optimization objective that you really care about. But Bayesian logistic regression instead optimizes a quantity like that. Right? It's this sort of maximum likelihood thing, and then with this two-norm penalty thing that we saw previously. You might be wondering, is this the right optimization function to be optimizing? Okay, or do I maybe need to change the value for lambda to change this parameter? Or should I maybe really be switching to a support vector machine optimization objective? Okay. Does that make sense? So the second diagnostic I want to talk about is, let's say you want to figure out, is the algorithm converging? Is the optimization algorithm converging? Or is the problem with the optimization objective I chose in the first place? Okay. So here's the diagnostic you can use. Right. So just to reiterate the story, right? Let's say an SVM outperforms Bayesian logistic regression, but you really want to deploy Bayesian logistic regression for your problem. Let me let theta subscript SVM be the parameters learned by an SVM, and I'll let theta subscript BLR be the parameters learned by Bayesian logistic regression. So the optimization objective you care about is this, weighted accuracy criteria that I talked about just now. And the support vector machine outperforms Bayesian logistic regression. And so, the weighted accuracy on the support vector machine parameters is better than the weighted accuracy for Bayesian logistic regression. So, further, Bayesian logistic regression tries to optimize an optimization objective like that, which I've denoted J of theta. And so the diagnostic I'll choose to use is to see if J of SVM is bigger than or less than J of BLR. Okay, so I'll explain this on the next slide. So we know two facts. We know that, we know one fact. We know that the weighted accuracy of the support vector machine, right, is bigger than this weighted accuracy of Bayesian logistic regression. So in order for me to figure out whether Bayesian logistic regression is converging or whether I'm just optimizing the wrong objective function, the diagnostic I'm going to use is I'm going to check if this equality holds true. Okay? So let me explain this. So in case one, right, it's just those two equations copied over. In case one, let's say that J of SVM is indeed greater than J of BLR. J of theta SVM is greater than J of theta BLR. But we know that Bayesian logistic regression was trying to maximize J of theta. Right? That's the definition of Bayesian logistic regression. So this means that theta, the value of theta output by Bayesian logistic regression actually fails to maximize J, because the support vector machine actually returned the value of theta that does a better job out maximizing J. And so this tells me that Bayesian logistic regression didn't actually maximize J correctly, and so the problem is with the optimization algorithm. The optimization algorithm hasn't converged. Right? The other case is as follows, where J of theta SVM is less than or equal to J of theta BLR. Okay? In this case, what does that mean? This means that Bayesian logistic regression actually attains a higher value for the optimization objective J than does the support vector machine. But the support vector machine, which does worse on your optimization problem, actually does better on the weighted accuracy measure. So what this means is that something that does worse on your optimization objective, on J, can actually do better on the weighted accuracy objective. And this really means that maximizing J of theta, doesn't really correspond that well to maximizing your weighted accuracy criteria. And therefore, this tells you that J of theta is maybe the wrong optimization objective to be maximizing. Right? So just maximizing J of theta, it just wasn't a good objective to be choosing if you care about the weighted accuracy. Okay. Can you raise your hand if this makes sense? Okay, cool, great. Excuse me. So that tells us whether the problem is with the optimization objective or whether it's with the objective function. And so going back to this slide, the 8 fixes we had, you notice that if you run gradient descent for more iterations, that fixes the optimization algorithm. You try Newton's method, fixes the optimization algorithm. Whereas using a different value for lambda, that lambda times norm of theta squared thing, right, in the objective, fixes the optimization objective, and changing to an SVM is also another way of trying to fix the optimization objective. Okay? And so, once again, you actually see this quite often, that actually you see very often people will have a problem with the optimization objective and be working harder and harder to fix the optimization algorithm. That's another very common pattern. That the problem is in the formulation of J of theta, that often you see people just running more and more iterations of gradient descent, like trying Newton's method, and trying conjugate gradient, and trying more and more crazy optimization algorithms, whereas the problem was optimizing J of theta wasn't going to fix the problem at all. Okay? So this is another example of when these sorts of diagnostics will help you figure out whether you should be fixing the optimization algorithm or fixing the optimization objective. Okay. Let me think how much time I have. Let's see. Well, okay, yeah, fine. Let's do this. Just to show you one last example of a diagnostic. This is one that came up in my students in my work on flying helicopters. This one actually, this example is the most complex of the 3 examples I'm going to do today. I'm going to do it somewhat quickly, and this actually draws on reinforcement learning, which is something that I'm not going to talk about until closer to the end of the quarter. But this is sort of just a more complicated example of a diagnostic that I go over. What I'll do is probably go over this fairly quickly, and then after we've talked about reinforcement learning in the class, I'll probably actually come back and redo this exact same example because you understand it more deeply then. Okay? So, some of you know that my students and I fly autonomous helicopters. So how do you get a machine learning algorithm to design a controller for a helicopter? This is what we do, right? The first step was you build a simulator for a helicopter. So there's a screenshot of our simulator. This is just like a joystick simulator. You can fly a helicopter in a simulation. And then we choose a cost function. It's actually called a reward function, but for this actually I'll call it a cost function. Say J of theta is the expected squared error in your helicopter's position. Okay, so J of theta is maybe it's called expected squared error, just a squared error. And then we run a reinforcement learning algorithm. You learn about RL algorithms in a few weeks. You run a reinforcement learning algorithm in your simulator to try to minimize this cost function, to try to minimize the squared error of how well you're controlling your helicopter's position. Okay. Your reinforcement learning algorithm will output some parameters, which I'm denoting theta subscript RL, and you then go use that to fly your helicopter. So suppose you run this learning algorithm, and you get out a set of controller parameters, theta subscript RL, that gives much worse performance than a human pilot. Then what do you do next? And in particular, corresponding to the 3 steps above, there are 3 natural things you can try, right? You can try to, well, the bottom of the slide got chopped off. You can try to improve the simulator. Maybe you think your simulator isn't that accurate. You need to capture the aerodynamic effects more accurately. You need to capture the airflow and the turbulence effects around the helicopter more accurately. Maybe you need to modify the cost function. Maybe a squared error isn't cutting it. Maybe what a human pilot does isn't just optimizing squared error, but it's something more subtle. Or maybe the reinforcement learning algorithm isn't working. Maybe it's not quite converging or something. Okay. So these are the diagnostics that I actually use, that my students and I actually use to figure out what's going on. Actually, why don't you just think about this for a second and think what you do, and then I'll go on and tell you what we do. All right, so let me talk about how we do this and see whether it's the same as yours or not. And if you have a better idea than I do, let me know, and I'll let you try it on my helicopter. So here's a reasoning that I once went through, right? So let's say the controller output by our reinforcement learning algorithm does poorly. Well, suppose the following three things hold true. Suppose to the contrary, I guess. Suppose that the helicopter simulator is accurate. So let's say we have an accurate model of a helicopter. And let's suppose that the reinforcement learning algorithm correctly controls the helicopter in simulation. So we tend to run the learning algorithm in simulation so that the learning algorithm can crash the helicopter and it's fine, right? So suppose the reinforcement learning algorithm correctly controls the helicopter so as to minimize the cost function j of theta. And let's suppose that minimizing j of theta does indeed correspond to accurate or the correct autonomous flight. If all of these things held true, then that means that the parameters theta RL should actually fly well on my real helicopter, right? And so the fact that the learned controlled parameters theta RL does not fly well on my helicopter, that sort of means that one of these three assumptions must be wrong. And I'd like to figure out which of these three assumptions was wrong. Okay. So these are the diagnostics we use. First one is we look at the controller and see if it even flies well in simulation, right? So we'll simulate the helicopter that we did the learning on. And so if the learning algorithm flies well in the simulator, but doesn't fly well on my real helicopter, then that tells me the problem is probably in the simulator, right? That my simulator predicts the helicopter's controller will fly well, but it doesn't actually fly well in real life. So clearly the problem is in the simulator. And we should spend our efforts improving the accuracy of our simulator. Otherwise, let me write theta subscript human be the human control policy, right? So let's go ahead and ask a human to fly the helicopter. It could be in simulator, it could be in real life. And let's measure the mean squared error of the human pilot's flight. Right? And let's see if the human pilot does better or worse than the learned controller in terms of optimizing this objective function j of theta. Okay? So if the human does worse, if even very good human pilot attains a worse value on my optimization objective, on my cost function, than my learning algorithm, then the problem is in the reinforcement learning algorithm. Right? Because my reinforcement learning algorithm was trying to minimize j of theta, but a human actually attains a lower value for j of theta than does my algorithm. And so that tells me that clearly my algorithm's not managing to minimize j of theta, and that tells me the problem is in reinforcement learning algorithm. And finally, if j of theta, if the human actually attains a larger value for theta, if the human actually attains a larger value for j of theta, if the human actually has larger mean squared error for the helicopter position than does my reinforcement learning algorithms, but I like the way the human flies much better than my reinforcement learning algorithm. So if that holds true, then clearly the problem is in the cost function, right? Because the human does worse on my cost function, but flies much better than my learning algorithm. And so that means the problem is in the cost function. It means, oh, excuse me, I meant minimizing it, not maximizing it. It's typed on the slide. Because that means that minimizing the cost function, my learning algorithm does a better job minimizing the cost function, but doesn't fly as well as a human pilot. So that tells you that minimizing the cost function doesn't correspond to good autonomous flight. And what you should do is go back and see if you can change j of theta. Okay? So, and so for various reinforcement learning problems, if something doesn't work, often reinforcement learning algorithms just work, but when they don't work, these are the sorts of diagnostics we use to figure out should we be focusing on the simulator, on changing the cost function, or on changing the reinforcement learning algorithm. And again, if you don't know which of your three problems it is, it's entirely possible to spend 2 years or whatever changing building a better simulator for your helicopter. But it turns out that modeling helicopter aerodynamics is an active area of research. There are people writing entire PhD theses on it still. So it's entirely possible to go and spend 6 years and write a PhD thesis and build a much better helicopter simulator, but if you're fixing the wrong problem, it's not going to help. Excuse me. So quite often you need to come up with your own diagnostics to figure out what's happening in an algorithm when something is going wrong. Unfortunately, I don't know of what I've described are sort of maybe some of the most common diagnostics that I've used that I've seen to be useful for many problems, but very often you need to come up with your own for your own specific learning problem. And just to point out that even when the learning algorithm is working well, it's often a good idea to run diagnostics like the ones I talked about to make sure you really understand what's going on. Right? And this is useful for a couple of reasons. One is that diagnostics like these will often help you to understand your application problem better. So some of you will graduate from Stanford and go on to get some amazingly high-paid job to apply machine learning algorithms to some application problem of significant economic interest, right? And if you end up working on one specific important machine learning application for many months or even for years, one of the most valuable things for you personally will be for you personally to get an intuitive understanding of what works and what doesn't work in your problem. So right now in the industry, in Silicon Valley or around the world, there are many companies with important machine learning problems, and there are often people working on the same machine learning problem for many months or for years on end. And when you're doing that, when you're solving a really important problem using learning algorithms, one of the most valuable things is just your own personal intuitive understanding of the problem. Okay? And diagnostics like the sorts I talked about will be one way for you to get a better and better understanding of these problems. Turns out, by the way, there's sometimes Silicon Valley companies that outsource their machine learning. So there's sometimes, whatever, company in Silicon Valley, and they'll hire a firm in New York to run all their learning algorithms for them. And I guess I'm not a businessman. I personally think that's often a terrible idea, because if your expertise, if your understanding of your data is given to an outsourced agency, then if you don't maintain that expertise, if there's a problem you really care about, then it'll be your own understanding of the problem that you build up over months that'll be really valuable. And if that knowledge is outsourced, you don't get to keep that knowledge yourself. I personally think that's a terrible idea. But I'm not a businessman, but I'm just seeing people do that a lot. Let's see. Another reason for running diagnostics like these is actually for writing research papers, right? So diagnostics and error analyses, which I'll talk about in a minute, often help to convey insight about the problem and help justify your research claims. Excuse me. So for example, rather than writing a research paper, say, that says, oh look, here's an algorithm that works, so I built this helicopter that flies, or whatever, it's often much more interesting to say, here's an algorithm that works, and it works because of a specific component X, and moreover, here's a diagnostic, which is a justification that shows X was the thing that fixed this problem, that's what really made it work. Okay? So that leads me into a discussion on error analysis, which is often good machine learning practice. This is a way for understanding what your sources of errors are. So if I talk about error analyses, let me just check questions about this. Yeah?
What ended up being wrong with the helicopter?
Oh, don't know. Let's see. We've flown so many times. The thing that is most difficult on helicopters is actually building a I don't know. It changes all the time. Quite often it's actually the simulator. Building an accurate simulator for a helicopter is very hard. Yeah. Okay, let's talk about error analyses. This is a way for figuring out what is working in your algorithm and what isn't working. I'm going to talk about two specific examples. So there are many sort of AI systems, many machine learning systems that combine many different components into a pipeline. Right? So here's sort of a contrived example, but it's not dissimilar in many ways from the actual machine learning systems you see. So let's say you want to recognize people from images. This is a picture of one of my friends. So you take its input a camera image, say, and you often run it through a long pipeline. So for example, the first thing you might do may be pre-process the image, remove the background. So remove the background. And then you run a face detection algorithm, some machine learning algorithm to detect people's faces, right? And then, let's say you want to recognize the identity of the person, right? This is your application. You then segment out the eyes, segment out the nose, and have different learning algorithms to detect the mouth and so on. I know, she might not want to be my friend after she sees this. And then having found all these features based on, what the nose looks like, what the eyes look like, whatever, you then feed all the features into logistic regression algorithm, and your logistic regression or softmax regression or whatever will tell you the identity of this person, okay? So this is what error analysis is. You have a long, complicated pipeline combining many machine learning components. Many of these will be built using learning algorithms. And so it's often very useful to figure out how much of your error can be attributed to each of these components. Right? So what we'll do in a typical error analysis procedure is we'll repeatedly plug in the ground truth for each component and see how the accuracy changes. So what I mean by that is, figure on the bottom left, bottom right, let's say the overall accuracy of the system is 85%. Right? Then I'd like to know where my 15% of error comes from. And so what I'll do is I'll go to my test set and I'll actually code in, I'll actually implement my correct background removal. So I actually go in and give my algorithm what is the correct background versus foreground. And if I do that, let's color that blue to denote that I'm giving that the ground truth data in the test set. Let's say my accuracy increases to 85.1%. Okay? And now I'm going and give my algorithm the ground truth face detection output. So I'll go in and actually on my test set, I'll just tell the algorithm where the face is. And if I do that, let's say my algorithm's accuracy increases to 91%, and so on. And then I'll go through each of these components and just give it the ground truth label for each of the components. Because say, like the nose segmentation algorithm is trying to figure out where the nose is. I just go in and tell it where the nose is so that it doesn't have to figure that out. And as I do this for one component through the other, I end up giving it the correct output label and end up with 100% accuracy. And now you can look at this table. I'm sorry, this is cut off on the bottom. It just says logistic regression 100%. Now you can look at this table and see how much getting the ground truth labels for each of these components could help boost your final performance. In particular, if you look at this table, you notice that when I added the face detection ground truth, my performance jumped from 85.1% accuracy to 91% accuracy. Right? So this tells me that if only I can get better face detection, maybe I can boost my accuracy by 6%. Whereas in contrast, when I say plugged in better, background removal, my accuracy improved from 85 to 85.1%. And so this sort of diagnostic also tells you that if it goes to improve the system, it's probably a waste of your time to try to improve your background subtraction, because even if you got the ground truth, this gives you at most 0.1% accuracy. Whereas you could do better face detection, maybe there's a much larger potential for gains there. Okay? So this sort of diagnostic, again, is very useful because if it goes to improve the system, there are so many different pieces you can easily choose to spend the next 3 months on. Right? And choosing the right piece is critical, and this sort of diagnostic tells you what's the piece that may actually be worth your time to work on. There's sort of another type of analysis that's sort of the opposite to what I just talked about. The error analysis I just talked about tries to explain the difference between the current performance and perfect performance, whereas this sort of ablative analysis tries to explain the difference between some baseline, some really bad performance, and your current performance. So for this example, let's suppose you built a very good anti-spam classifier by adding lots of clever features to your logistic regression algorithm. Right? So you added features for spelling correction, for sender host features, for email header features, email text parser features, JavaScript parser features, features from embedded images, and so on. So now let's say you have a pretty decent system, and you want to figure out how much did each of these components actually contribute. Maybe you want to write a research paper and claim this was the piece that made the big difference. Can you actually document that claim and justify it? So in ablative analysis, here's what we do. So in this example, let's say that simple logistic regression without any of your clever improvements get 94% performance. And you want to figure out what accounts for your improvement from 94 to 99.9% performance. So in ablative analysis, instead of sort of adding components one at a time, we'll instead remove components one at a time to see how it breaks. So start off with your overall system, which is 99% accuracy. And then we'll remove spelling correction and see how much performance drops. Then we'll remove the sender host features and see how much performance drops, and so on. Right? And so in this contrived example, you see that, I guess, the biggest drop occurred when you remove the text parser features. And so you can then make a credible case that, you know, the text parser features were what really made the biggest difference here. Okay? And you can also tell, for instance, that I don't know, removing the sender host features on this line, right? Performance dropped from 99.98 to 98.9%. And so this also means that in case you want to get rid of the sender host features to speed up computation or something, that would be a good candidate for elimination. Okay?
Are there any guarantees that if you shuffle around the order in which you drop those features that you'll get the same?
Yeah, so just a question. What if you shuffle the order in which you remove things? The answer is no. There's no guarantee you get a similar result. So in practice, sometimes there's a fairly natural ordering for both types of analyses, the error analysis and the ablative analysis. Sometimes there's a fairly natural ordering in which you add things or remove things. Sometimes there isn't, and quite often you either choose one ordering and just go for it, or and don't think of these analyses as sort of formulas that are cast in stone. You feel free to invent your own as well. Like, like one of the things that's done quite often is take the overall system and just remove one and then put it back, then remove a different one, then put it back. So all of these things are done. Okay. So the very last thing I want to talk about is sort of just general advice for how to get started on a learning problem. So here's a cartoon description on maybe two broad approaches to get started on a learning problem. First one is you can carefully design your system. So you spend a long time designing exactly the right features, collecting the right data set, and designing the right algorithmic structure. Then you implement it and hope it works. Right? The benefit of this sort of approach is you get maybe nicer, maybe more scalable algorithms, and maybe you come up with new elegant learning algorithms. And if your goal is to contribute to basic research in machine learning, if your goal is to invent new machine learning algorithms, this process of sitting down and thinking deeply about the problem, that is sort of the right way to go about it. Is think deeply about a problem and invent new solutions. Second sort of approach is what I call build and fix, which is we implement something quick and dirty, and then you run error analyses and diagnostics to figure out what's wrong, and you fix those errors. The benefit of this second type of approach is that it'll often get your application working much more quickly. And especially for those of you, if you end up working in a company, and sometimes if you end up working in a company, very often it's not the best product that wins. It's the first product to market that wins. And so there's, especially if you're in industry, there's really something to be said for building a system quickly and getting it deployed quickly. And the second approach of building a quick and dirty, I don't say hack, and then fixing the problems will actually get you to a system that works well much more quickly. And the reason is, very often it's really not clear what parts of a system are easy or difficult to build, and therefore what you need to spend lots of time focusing on. So there was that complicated example I talked about just now, right? For identifying people, say. And with a big complicated learning system like this, a big complicated pipeline like this, it's really not obvious at the outset which of these components you should spend lots of time working on, right? And if you didn't know that pre-processing wasn't the right component, you could easily have spent 3 months working on better background subtraction, not knowing that it's just not going to ultimately matter. And so the only way to find out what really works is implement something quickly and find out what parts, and find out what parts are really the hard parts to implement, and what parts are hard parts that could make a big difference in performance. In fact, I'll say that if your goal is to build a people recognition system, a system like this is actually far too complicated as your initial system. Maybe after you prototype a few systems, you may converge to a system like this, but if this is your first system you're designing, this is much too complicated. Also, this is a very concrete piece of advice, and this applies to your projects as well. If it goes to get a working application, step one is actually probably not to design a system like this. Step one is for you to plot your data. And very often, if you just take the data you're trying to predict and just plot your data, plot X, plot Y, plot the data every way you can think of, half the time you look at it and go, gee, how come all those numbers are negative? I thought they should be positive. Something's wrong with this data set. And about half the time you find something obviously wrong with your data or something very surprising. And this is something you find out just by plotting your data, and that you won't find out by implementing these big complicated learning algorithms on it. Plotting the data sounds so simple. It's one of the pieces of advice that lots of us give, but hardly anyone follows. So you can take that for what it's worth. Let me just reiterate, what I just said here may be bad advice if your goal is to come up with new machine learning algorithms, right? So for me personally, the learning algorithm I use the most often is probably logistic regression because I have code lying around. So give me a learning problem, I probably won't try anything more complicated than logistic regression on it first. It's only after trying something really simple, figure out what's easy, what's hard, then you know where to focus your efforts. But again, if it goes to invent new machine learning algorithms, then you sort of don't want to hack up something and then add another hack to fix it and then hack it even more to fix it, right? So if it goes to do novel machine learning research, then it pays to think more deeply about the problem rather than follow this specifically. Shoot, you know what? All right, I'm starting to run late, but I just have 2 more slides, so let me go through these quickly. And so this is what I think of as premature statistical optimization, where quite often, just like premature optimization of code, quite often people will prematurely optimize one component of a big complicated machine learning system. Okay. Just 2 more slides. This is a sort of cartoon that highly influenced my own thinking. It was based on a paper written by Christos Papadimitriou. This is how development or progress or research often happens, right? Let's say you want to build a mail delivery robot. So I've drawn a circle there that says mail delivery robot. It seems like a useful thing to have, right? Free up people to deliver mail. So, well, to deliver mail, obviously you need a robot to wander around indoor environments, and you need a robot to manipulate objects, to pick up envelopes. And so you need to build those 2 components in order to get a mail delivery robot. And so drawing those 2 components and little arrows to denote that obstacle avoidance is needed or will help build your mail delivery robot. Well, to do obstacle avoidance, clearly you need a robot that can navigate, and you need to detect objects so you can avoid the obstacles. Now, we're going to use computer vision to detect objects, and so we know that lighting sometimes changes, right? Depending on whether it's the morning or noontime or evening, this is lighting causes the color of things to change. And so you need an object detection system that's invariant to the specific colors of an object, right? Because lighting changes, say. Well, color, right, this RGB values is represented by 3-dimensional vectors, and so you need to learn when 2 colors might be the same thing. When 2, visual appearance of 2 colors may be the same thing as just the lighting's change or something. And to understand that properly, we're going to go off and study differential geometry of 3D manifolds, because that helps us build a sound theory on which to develop our 3D similarity learning algorithms. And to really understand the fundamental aspects of this problem, we have to study the complexity of non-Riemannian geometries. And on it goes until eventually you're proving convergence bound for sampled non-monotonic logic. I don't even know that because I just made it up. Whereas in reality, chances are that link isn't real. Color invariance is going to just barely help object recognition. Maybe, I'm making this up. Maybe differential geometry was hardly going to help 3D similarity learning, and that link is also going to fake. Okay, so each of these circles can represent a person or a research community or a thought in your head. And there's a very real chance that maybe there are all these papers written on differential geometry of 3D manifolds, and they're all written because some guy once told someone else that it'll help for 3D similarity of learning. And it's like a friend of mine told me that color invariance will help in object recognition, so I'm working on color invariance, and then I'm going to tell a friend of mine that his thing will help my problem, and he'll tell a friend of his that his thing will help with his problem. And pretty soon you're working on convergence bound to sample non-monotonic logic when in reality none of these will see the light of day of your mail delivery robot. Right? I'm not criticizing the role of theory. There are very powerful theories like the theory of VC dimension, which is far, far, far to the right of this. So VC dimension is about as theoretical as it can get. And it's clearly had a huge impact on many applications and has dramatically advanced the state of machine learning. Another example is theory of NP hardness. That's again, it's about as theoretical as it can get. This has such a huge application on all of computer science, the theory of NP hardness. But when you're off working on highly theoretical things, I guess, to me personally, is important to keep in mind, are you working on something like VC dimension, which is high impact? Are you working on something like convergence bound for sample non-monotonic logic, which you're only hoping has some peripheral relevance to some application? Okay. For me personally, I tend to work on an application only if for me personally, this is a personal choice, I tend to trust something only if I personally can see a link from the theory I'm working on all the way back to an application. And if I don't personally see a direct link from what I'm doing to an application, then then that's fine. Then I can choose to work on theory, but I wouldn't necessarily trust that what the theory I'm working on will relate to an application if I don't personally see a link all the way back. Just to summarize, one lesson to take away from today is I think time spent coming up with diagnostics for learning algorithms is often time well spent. It's often up to your own ingenuity to come up with the right diagnostics. And just when I'm working on machine learning algorithm, it's not uncommon for me to spending like between a third and often half of my time just writing diagnostics and trying to figure out what's going right and what's going wrong. Sometimes it's tempting not to, right? Because you want to be implementing learning algorithms and making progress. You're only spending all this time implementing tests on your learning algorithms. It doesn't feel like you're doing anything. But when I implement learning algorithms, at least a third and quite often half of my time is actually spent implementing those tests and figure out what to work on. And I think it's actually one of the best uses of your time. Talk about error analyses and ablative analyses, and lastly, talked about different approaches and the risks of premature statistical optimization. Okay, sorry about running over. I'll be here for a few more minutes if you have questions. Let's close today.